The talk that I'm going to give you is where we'd like to explore whether European supercomputers are actually ideal to train large language models. So let's have a look at that. I'm from Vienna, and in Vienna we have the Vienna Scientific Cluster, which is a tier 1 system, and I'll show you how that would work on such a system. But first, let's just get that out of the way. I'm sure you know already, but what large language models can be used for. I'm just putting that into my talk, even if you know, because it's very important to know what your application actually involves, because only then you can choose the right model for your application. We've got fantastic models that are really large, as you've heard in the previous talk already. That can do lots of general things, but maybe that's not what you need, and maybe you don't have to go as big. So it's really important to know what you want to achieve and then choose your model accordingly. There are a lot of expressions out there, and I just want to bring in a little bit of clarity so you know when do you actually need a lot of compute power, and what could you possibly even achieve with your workstation or even laptop? Well, you've all heard or are familiar with prompt engineering, I'm sure, which is claimed to be, even if it's a little bit of a hype, to be the next big skill that you need in job applications. Well, prompt engineering is something that you can obviously achieve on your own machine. You do not need a lot of compute power for that. It already changes a bit if we go one step further. If you want to use large language models for your specific use case, for example, as a business, then you might want to go the RAG approach, which I'll talk a little bit about in the next slide. You don't necessarily need a lot of compute power, but it could already be helpful at this stage. And then if you go further down the line, if you want to fine-tune your very own model for your application, this is where it actually really gets tricky. And there are a lot of tricks that you could use to achieve a lot with little compute power, but this is where you actually already need some substantial computational abilities, and this is where you'd like to switch to one of the supercomputing centers possibly. And then of course you could even train your large language model from scratch, do the whole thing yourself, go all the way. Well, this is when you actually need a tier O system like Lumi or Leonardo, which you'll also hear more about today. So just to give you an overview briefly, what is the difference between the RAG approach and fine-tuning? Both of these expressions are out there, but when do you use which of them? Well, RAG, or what's also known as retrieval augmented generation, is actually a two-step approach. And if you go for this approach, you don't change the weights, the parameters of your model at all. So what you do basically is you take your data repository, what you have, and data that you'd like to pass to the model. You let the model see that data. So you need to bring that into some sort of numeric representation. You need to tokenize it. And then you feed that to your model. So the response that you get from your model comes in two forms. So first, the model has a look at the data to get the facts straight. So it gets the factual context out of the data, and then it generates text like it is trained to do, like you know from ChatGPT, right? So the idea here is that you'd like to reduce hallucinations significantly, but nonetheless get a reasonable response. So for example, if you're in a company and you'd like to get some information on, let's say, if you still have some days of holiday available, vacation available, you might ask your company's GPT, do I still have a holiday available, and can I take half a day off next Tuesday? Well, the model should not hallucinate in such a situation. You do want to get the facts right. And this is where a RAG approach would be useful, because the model then could tell you, well, yes, according to what I see in your data, you still have holidays available, so you could take a day off. However, you can't take half a day off because this is not our company policy. Okay, so this is where you could use a RAG approach. However, if you want a certain type of language in that response, then you'd have to go even further and do some fine-tuning. And this is where you actually change the weights of your model. So in that case, you provide your data to the model and also do some training according to that data. And you update the weights to a certain degree so that it gets to know that specific data. And this is used when you want a certain tone, a certain lingo that is used maybe in that specific domain or in that company. For example, just recently, we had a customer at EuroCC Austria that was a law firm. They tried the RAG approach before to not train a model, but to get a model to find similar approaches to a certain case in law. Well, that worked. It got the facts right, but there were just a few things off. The language was not the type of language that you use in law, and as you know, that's a very specific type of language. And the other thing was that, in inverted comma, logic was missing in there. So the way you would argue a case and the way you would build up a law case, okay, so that was missing. So what we had to do in the end, and that's still ongoing, is we had to do a fine-tuning, okay? So this would be the classic approach. And then in the end, and this is what we'll also do in this specific case, you have to do both. So first you fine-tune your model, and then you also use the RAG approach. And with a RAG approach, you also have that benefit that if your underlying data changes, and that changes constantly, obviously, you heard that in the previous talk, it always depends on when the model was changed, which information it has seen. Well, with a RAG approach, you can quickly update that. But with fine-tuning, that takes time. You might not want to do that on a weekly basis, but maybe only once a year, okay? So this is when you use these two approaches. Now, there's this website that you might already know. It's called Hugging Face. It's a fantastic website because they basically offer all types of models and data sets that you can play around with. And they have this huge repository that you can access. But they're not the only ones. I just picked them because they're popular, they're well known. But you could also find something similar maybe with NVIDIA or other big players out there. But let's just have a look at the Hugging Face website so you know what I'm talking about. And I'll just quickly switch to there. So here we have the Hugging Face website. What I'd like to have a look at in this case are the models. So I'm going to the models, and you can already see there's a lot of fantastic filtering that you could use here depending on the use case that you have. So for example, if we're talking about natural language processing, then we might want some text generation. I can filter that accordingly. If you look at the training models, you can already see some big names out there, like the Meta Llama 3 and so on. What I'm actually after, or if let's have a look at the Meta Llama 3, or actually I'll just filter with Meta. Let's just get the Meta models since they're so popular. Here we've got the Meta Llama 3 70 billion instruct. And here you get this, what is called a model card. So you get all the relevant information about licenses that might apply or constrictions that might apply if you use that model. You also get some information on what it can use if you want to use certain ways to actually fine-tune the model. So here we know that this can use mixed precision and yeah, the size of the model is also there. And if you scroll down, you can see that you only get access to that model. I need to scroll down even further if you actually apply to get that. So if you fill that out, that might take a day or so, and then you get an access key and you can actually fine-tune this model. Well, actually, I haven't done that for the Meta Llama 370B yet. Still need to do that, but I've done so for the Meta 270B. Let's see if it's still around. Here's somewhere. Yeah, there it is. And what you might want to do is you might want to copy the model name. I'll show you where you can use that later, okay, if you want to fine-tune your model. You can also play around with the data sets here, have a look at these, and they've also got a fantastic repository on documentation. So check out the Hugging Face website if you've not done so yet. Okay, let me head back to my presentation. That is, if I can find it. There it was. So right, now we've picked the right model for our specific use case. You'll see how we'll use that later. And now you need to prepare your data. Now, this talk is not about data preparation in itself, but be aware if you have an actual use case, this is where you'll spend the most time. And it's good that if you spend the most time there, because the principle is here as it is in many cases. It's garbage in, garbage out. So if your data is no good, your model will be no good as well. So really do spend time in making sure your data is of a high quality, because time spent here is not wasted. So I'd just like to emphasize that. Now, if you have a look at a supercomputer, supercomputers have a typical setup. I'll just briefly mention that as well. This applies to all supercomputers. They're all very similar. So basically, you log onto a login node. You can usually do that via SSH. In our case, in Vienna, we can also use a Jupyter Hub. We could also hook up our IDE, like VS Code, for example. That's what I very often do. In that case, I'll use the Jupyter Hub because it's just a little bit more appealing visually. And then basically when you prepare your model and you prepare your data, you can do that on the login node, but you don't do any heavy lifting there, any heavy computations. For that, you send your model to the actual compute nodes, and you ask for a certain amount of compute power there. And then your job that you send off is scheduled via a batch system. So depending on the priority that you have as a user, and also depending on the time it takes to complete your job and the resources that you asked for, you'll have to wait until your job begins to run. Okay, so it is then scheduled. So it is important to also mention if you have an idea of how long your job takes, so the batch system gets a better idea of where to squeeze you in. And then as soon as your job runs, it runs, so nothing to do for you then. And basically in the end, once it's done, you get an output file where you can see that it has completed, or should it have failed for some reason, you get that information as well. So in the Vienna Scientific Cluster, we've got two supercomputers, VSC4 and VSC5. And in connection with AI applications, and especially large language models, VSC5 is the go-to supercomputer there. The reason for that are these lovely things here. That's a GPU. It's an NVIDIA A100 GPU. So what we have there is we have 60 GPU nodes, each with 2 of these A100 graphic cards. So we'll be using that in a minute. We also have A40, which can also do quite substantial heavy lifting. However, they are slower, so you'll probably get about half. Oh, yeah, you'll take twice as long if you use these, even if they are the same memory-wise. As soon as you use GPUs, however, you'll find out that you'll run into a few problems. Well, it could be that either your data or your model is too large to fit into the memory of a GPU. Now, with data, it's not that much of a problem, and you'll see that on the next slide. But with a model that is too large, you really are constrained then, okay? And it's important to figure out if your model fits into your memory or not. There are tools out there. There's actually one tool out there. I haven't got the link right now. You can Google it. It's from a Hugging Face user that can tell you, or just gives you an estimate whether a certain model fits into the memory of your architecture or not. So the reason being, if you just do a bit of simple maths, if you take a model size of 7 billion parameters, for example, the Mistral 7B in this case here, you already have to be aware that each parameter, if you want to get the bytes of that, you have to multiply it by 4, obviously. So you know that it takes 28 gigs of GPU memory as it is the model, if you don't apply any tricks whatsoever. And in our case, we have two GPUs there. So if it comes to the RAM that you want, not the VRAM, but the RAM, you will need at least twice as much, okay? So just keep that in mind before you try to train a model. Now, if your data doesn't fit in memory, that's not such a big problem because you can use data parallelism. So if you have many GPUs available, if you go on a multi-GPU training scenario, then you can split up your data. This is done more or less automatically for you without you having to do anything with the different packages that there are out there for Python. So basically the model that you take, if we go back to our Llama model, that would fit on every GPU, in the memory of every GPU, and you get the whole model in there per GPU. And just your data is split up. Now, if the model doesn't fit in a GPU, well, it gets a bit messy, as you can imagine, because we've got to split up our Llama in that case, and you only put parts or shards of that model in a GPU. Now, this is where it gets a bit tricky. There are, however, ways to do that without being super fit in mathematics or parallel programming. So the tools that you get, especially with the Hugging Face Accelerate library, help you a lot there. So basically there are three ways in the Hugging Face Accelerate library. One is called Deep Speed. That will help you split up that model. The other one is called FSDP. And then there's that third one it's offered by NVIDIA. Forgot its name right now, but we'll have a look at that in a minute, okay? So this is how you'd have to split up these models. You can split up the model in two ways. Well, one is called pipeline parallel, and one is called tensor parallel. Well, in pipeline parallel, you split up the model layer by layer, or maybe you'll bundle a few layers together, but a couple of layers go on one GPU, the next couple goes on the next GPU, and so on. However, you have to be aware that the largest layer still needs to be able to fit into the memory of your GPU. If not, you'll have to go tensor parallel. And this is where you really split the actual tensors of that you have within your models with all the weights. And then you only train parts of these tensors, and the whole model is then synchronized on one GPU. So all the weights are then synchronized, all the gradients are synchronized, and then that is spread again onto the other shards as well. Now, if you fine-tune a model, here we have the Vienna Scientific Cluster, but that basically applies to any other cluster as well. What you need, obviously, is access to that specific cluster. You need a working environment. Very often, supercomputing centers provide these for you. You need your training data. That makes sense. And then you need your Python scripts, config files, a Slurm script, and then you can actually do that. So let's have a look at that, how this is done on the Vienna Scientific Cluster. So if I switch back, I'm already logged in there on the Jupyter Lab. And what we have there is basically what you need is you need your script. That's the Slurm script. So here, basically, I just say what I'd like, which resources I'd like. Well, I'd like 8 nodes of GPUs. Here we have the GPUs. And each of these nodes has 2 A100 GPUs. And if I scroll down in my script there, I've got my accelerate launcher. This is what the Hugging Face what triggers the Hugging Face accelerator, what starts that for me. And what it needs a config file. And we're using deep speed in this case in connection with some other tricks like parameter efficient fine tuning called LoRa. And we also use some quantization to make the model smaller so it fits more easily and we don't have to use so much compute power. And in this case, then I'll also pass which model I'd like to train. I'd like to train the Lava 270B. I've got the access key for that, so it's all good. On this specific, it's just a more or less a toy data set. Not too small, as you can see, but nonetheless, it's just a toy data set from the Hugging Face hub. Then you basically just need your Python script. In this case, I've got 2 scripts, one training script and the others with the utils to make it a bit more readable and a bit more general as well. And that's it. Then I can send off that job. So I'll just go sbatch. What's it called? It's called run heft q LoRa deep speed. That's it. And then I'll send that off and that job is submitted. Now, if I would like to have a look at what's going on in the background, I can do so. And you can see I've got 2 jobs running. One is the Jupyter Hub that I'm on right now, and the other one is pending in the queue. So this is the one where I asked for 16 GPUs in total. Actually, I wouldn't have needed as much. I could have sent that off with, would have been enough with 6 GPUs probably, so 3 nodes. But yeah, we sent it off with much more, and they scale pretty perfectly. So if I use twice as many resources, it finishes twice as fast, basically. Okay, so this is how you would send off a job like that. Now, if it comes to inference of your model, so that is fine-tuning now in the background as we speak, or as soon as the job runs. When it comes to inference, however, and you want to use these models in earnest then to ask it questions or generate text or whatever, then supercomputers are not the perfect infrastructure for that. As you could see, my job was still pending, and that might even take a couple of hours. In inference, you don't want to wait around till you get an answer, right? So if you want to actually host a model, you need to go somewhere else. Again, you could use the Hugging Face platform to maybe even host your model if you're a paying customer, or somewhere else, or do it on premise, whatever. But supercomputers are certainly not the place to do that. And even in inference, you need quite some compute power, not as much as in fine-tuning for sure, but you still need to somehow fit your model into the memory of a GPU. Now, the EuroCC project can help you get access to supercomputers. We've got 32 national competence centers, and I'm here from rainy Austria. That's just one of these supercomputing centers. You could also contact the one in Greece if you need compute power, and we should be able to help you with that. If you need more compute power than these tier 1 systems, as we have, for example, in Vienna, you might go to the really big machines like Lumi, which you'll hear more about today, which is Europe's most powerful supercomputer, or Leonardo, which is the second in Europe, where you could actually even, train your models from scratch. Now, to get access to the other larger systems, there are calls for proposals, and I've got them here in these links. There are different forms of access that you could get. You can get the development access pretty easily, and then if your model works well there, this is just to familiarize yourself with the system. If it works well and you can prove that it scales, you can apply for the next larger access. So basically, just to wrap up, RAG is an approach that is super useful, where you just need compute power to tokenize the data, the underlying data. You might not need a supercomputing center for that. However, they can be of help. But as soon as you want to do more than that, as soon as you want to fine-tune or even train a model from scratch, you really need more than just your workstation at home or in your office. EuroCC is there for you. It can give you access to compute power, or help you apply for that. And what EuroCC can also give you is access to training. So we've got this training coming up in Vienna in July, large language models on supercomputers. I might just post that in the chat. So feel free to apply from that if you're from one of the European countries that are part of the EuroHPC joint undertaking. So that's European Union plus a few more. Feel free to apply or to register for that. This will be on the 3rd and 4th of July. And with that, I'd like to thank you. You can also stay in touch with us if you wish to follow us here in Vienna. And yeah, thank you for listening.